there's several oxides that lead to acidification. You all know what acidification is. Basically, when we burn, oxidize carbon dioxide is acidifying. If we weren't so worried about global climate change, we could still be worried about carbon dioxide because it's going to acidify the oceans. So far we think that's a smaller problem than climate change, but it's still quite a big problem. The oxides of sulfur and nitrogen are more potent acidifying agents. And this is a problem that was noticed in the 60s and the 70s first, acidification. Fishes started dying. And Swedish researchers figured out that this was due to acidification, and that the problem was coming from the Ruhr in Germany and Britain, to some extent France, were the major sort of sources of industry, and they were burning coal. And so Swedish researchers traveled to the, to the continent and tried to persuade other researchers. And of course the Brits said, surely, if you think the problem is coming from here, our fishes will be dying first, and they're not. So you probably got some other problem up there in Sweden. I mean, it's a pretty cold and nasty place anyway. Why would the fishes want to, to live up there? And it actually took a decade or so of science to figure this out. And people like Per-Inge Grenfeldt here at IVL in Gothenburg were quite central in this. And eventually this became a very large sort of multinational effort where researchers and politicians have spent decades working out how much comes from where and who should reduce the most. And I'll show you this map. So this map gives a little image of why Swedish researchers kind of noticed this problem first. The bedrock in Sweden is made of granite, and the ecosystem consists of pine trees and fir trees. And so this rock has very little buffering capacity. It's not like limestone. You see, England here, for instance, is basically made out of chalk, sedimentary chalk, a rock with a lot of calcium in it. And you pour acid rain on it, and nothing much happens. It's all absorbed by the calcium. Calcium will form calcium sulfate, for instance, if you pour sulfuric acid on it. And it is buffered, basically. So that's why the English trout were still happy in spite of all the acid deposition. So the sources of sulfur and also NOx were down here. Actually, a lot of the wind was kind of blowing northwest, so there was a disproportionate amount of deposition over Scandinavia. And then the Scandinavian bedrock has no calcium, so there was little buffering capacity. And our ecosystems with marshes and pine trees are naturally acid on top of this, so that we already have lakes that are kind of, slightly sour and acid, and a little more deposition kind of pushed them over the edge, and trout started dying, and other sensitive fishes started dying. So we noticed this problem here. And all that, it took some time to persuade, particularly industry, of course, but I mean, first you had to persuade the scientists like in Britain and France and Germany. Then in Germany also, you can see there's some sensitive spots here. They had a big problem of what they call Waldsterben, which was the death of trees, basically. And so that was also shown to be a part of the same problem. And there's a lot of complicated ecology behind this. But some of the fundamentals are this, basically, are the bedrock. So, go back to this. Sweden was very heavily affected. And we care also about our lakes. I mean, this is a country where most people actually have roots in the countryside, and a very large proportion of people do spend time in the countryside and do kind of care about the fishes. And so there's a lot of, there was a lot of interest in this. And we got the highest sulfur taxes in the world. I think that was the last slide I showed to you in my introductory lecture. The sulfur trading that they had in the US. With a price, they were so pleased about this, the price was not like $1,000 per ton, but just 100. Well, we have a tax, and the tax is 3,000 euros per ton. So it's a tax that is much higher than the worst case scenario that they were considering for this. So it's about 30 times as high as the price of tradable permits. And the goal of that US program was to cut emissions in half. The goal of the Swedish program has been sort of 99.5% or something. I mean, it's like, it's a completely different scenario. We're being, well, you could say we're being much more ambitious. I don't want you to go away thinking that Swedes are always more environmental, because California had catalytic converters on Volvo cars a decade before we had them in Sweden. So we just care about different problems. California and San Francisco, they cared a lot about smog. Smog comes from lots of people, lots of cars, and lots of sunshine. And we don't have that in Sweden. None of those three things, right? But we have a lot of lakes with trout that are kind of already on the verge of dying, so we care more about that problem. I think this is important to say that, you know. By the way, this little detail here, there's nothing that impresses economists more than if you can calculate what a tax in, you know, kilos of sulfur, how much that is in kilos of sulfur dioxide. Because economists have a complex about not knowing a lot of natural science. We became economists because we didn't, you know enough math to become physicists or something. And of course, the atomic weight of oxygen is roughly 16, and that of sulfur is roughly 32. So you can work out the molecular weight of sulfur dioxide is roughly 64, and that of sulfur 32, so the price of sulfur is converted into a price of sulfur dioxide by dividing by half. That's much easier than going from carbon to carbon dioxide, which gives you some sort of number like 3.6 or something. Anyway, we had this outrageously high sulfur tax in Sweden because we really care a lot about acidification. Now we also wanted to do something about nitrogen. But nitrogen is really different from sulfur, because the sulfur dioxide that comes out of a chimney is basically formed because there was sulfur in the fuel, right? So you got fuel. The chemical formula, if you'll excuse me, the people who know better, the chemical formula of fuel is roughly CH, right? CH something, like N here. I mean, fuels vary a little bit. You burn that, and you get carbon dioxide from the C and water from the H. But there is also a little sulfur in there. It's just a pollutant. It's really, you don't want it there. It's not, you don't have it because it's fuel value. And so that sulfur, when it gets burnt, turns into sulfur dioxide. So you want to know how much sulfur comes out of a chimney. You see a chimney over there. You can see one out the window there, actually. Well, it's easy. You just figure out how much fuel they burnt. What was the percentage of sulfur? Say it was like 1%. And then, you can figure out how much sulfur dioxide came out of the chimney, and you can put a tax on it. You can't put a tax on something if you don't know how much it is. But people are very fussy about money. So a tax has to be like exact. Right? And if some of the sulfur is captured, you can throw chalk or other stuff in the furnace and capture some of the sulfur in filters and all kinds of stuff. Well, then you capture that, and it's left in your filter, and you can kind of measure that too. And you can say, okay, we don't want to pay for this stuff because we captured it. So what you do is you calculate the amount of sulfur that comes out of the, that would have been in the fuel and would have been burnt. You deduct the amount you captured, and you pay tax on the rest. Easy. However, for nitrogen, for NOx, not very easy. Because the NOx, there can be a little nitrogen in the fuel. That's mainly if you burn wood. But a lot of the right, so the reaction that you want is this, basically, which produces carbon dioxide and water. But then when you have a very hot place, like a furnace, or inside a car motor as well, you have a secondary reaction that goes on. There is nitrogen, there is oxygen in the air, and those two together will form NOx, just because it's hot. So this is a secondary reaction, and as nature would have it, it's a very nonlinear one. So the amount of NOx formed here in this reaction, and NOx, I mean, is a simplification. There is NO, NO2, N2O, and so on. There's several chemicals there. But there's lots of reactions, in fact. But these reactions are very nonlinear in temperature. So if the temperature is 10% higher, it could be twice as much or something. So this means that you have to care about the distribution of temperature inside the furnace. And you can have a furnace where it's really hot someplace, and then it's a little bit less hot on the side because of the wall of the furnace or whatever, because of the way the air runs through the way the air flows inside the furnace, the humidity, the size of the fuel particles. If you grind the coal a bit more finely, the air will flow differently. So you change the configuration of temperature inside, and you change the amount of NOx formed a lot. No, I go into all this detail because sometimes the details of the sort of the technology in nature interact with details of economics. And in this case, so there are things you can do. For instance, one measure that is often done with old furnaces is called exhaust gas recirculation, EGR. That is, you basically take a pipe from the exhaust and you kind of connect it to the flow of air in, and you let some of the hot exhaust air go back into the furnace and sort of burn it again. And this has a number of positive effects, but it can also have some negative effects. It changes the amount of NOx. And all this is so complicated that we talked, I mean, I had dozens of master's students, for instance, who do little studies on just one furnace, and they talk to the engineers, and the engineers would say, okay, we're going to try this, see what effect it has. And we were kind of like, what, try this? Can't you figure out what the effect's going to be? You're an engineer. And it's too complicated. So they try things. They try a similar thing on 2 or 3 different furnaces. It has a different effect. So the rules of thumb don't really work. And what is the conclusion of all this? Well, the conclusion is that you need to measure the amount of NOx in order to know how much NOx there is. We can't calculate it. And that's one conclusion. Another thing is that small fine-tuning, just exactly the amount of humidity and exhaust gas recirculation and the shape of the furnace and a number of other things will have a big effect. So you have these engineers and they're tinkering with the system, but if there's no measurement, then they don't know what they're doing. So then they wouldn't even bother to tinker with the system. But if they've got measurement, and that's, now the next thing to say is measurement is expensive. Right? It's a really complicated thing you put on the chimney. And so, particularly when they started this, you know, there's technical progress in that too. But when they started, this was a very expensive thing, and it would give you a reading every 5 minutes or every 15 minutes. The engineers would play with their dials, and they found that they could reduce emissions a lot. But only because they had the measurement. Otherwise they couldn't, because they don't know what they're doing. So measurement was really important, but measurement was expensive. So measurement was so expensive that you couldn't really do this for small plants. You'd only do it for the biggest plants. So now we get into one of the situations that Carolyn called partial regulatory coverage. That is, the authorities are going to cover some of the plants, the big plants, but not the small plants. So it's exactly a situation when you might want output-based allocation, because you're not taxing a whole industry, you're basically going to tax some. And you can think of this in it has very simple effects as well. Think of the Gothenburg energy plant, Göteborgs Energi. Those guys are really smart. If there was a big tax on big power stations and no tax on small power stations, guess what they'd do next time they build the power station? Build 2 small ones. Right? So that's why you can't really just have a straight tax. It works like this. The big plants, they pay the tax. And remember this, the other thing, we wanted a gigantic tax here. And a gigantic tax on some industries, and then no tax on the small companies, that wouldn't work. That wouldn't work for the reason I just said with the, you know, because in Gothenburg Energy would build small units. Also, we have Denmark quite close by. You could put some plants in Denmark and sell the electricity to Sweden, and the Danes have no tax on. So it wouldn't work for that reason either, and that brings you into this whole area that Carolyn was talking about. You could, of course, then start taxing the Danish electricity, but then that creates a whole lot of legal problems with the European Union, and it's hard to know which electricity exactly comes from which plant, and you know, it gets messy. So there was a whole series of practical reasons. Sweden is a small, open economy. We wanted to reduce NOx by affecting technology. Remember, there are 2 ways of reducing NOx. I could do this. Look. That is reducing output from the power plant. The room will be a little colder, and there will be less NOx. Right? But the Swedish policymaker didn't really want to reduce NOx by having colder lecture rooms and shorter showers, which would be like reducing output and consumption of the final good. They wanted to force the power plants to clean up their ovens, their furnaces. Because in fact, and that was another item on Carolyn's slides, the possibilities here technologically are enormous. Some plants emit, well, I'll show you, like 10 or 100 times more than others. So it seems that there's a lot you can do with technology. Whereas persuading people to, to take shorter showers is a pretty roundabout way of reducing NOx emissions. It works, but. So this is the way it actually works here. I'm not allowed to show you this, so don't remember any of the details, right? Okay, because these are confidential data, although they're actually, I think these are kind of old by now. But here you got a list of the individual plants. Yeah, it's very confidential. We're putting this all on YouTube. Then here are their NOx emissions, which are measured with this expensive measuring equipment, right? Every 15 minutes, real measurements. So first thing, some of my time I spend talking to other countries, researchers and people who are doing something about NOx. First question I ask is always, are the NOx emissions we're talking about in Belgium or wherever it is, are they actually measured, or is this like some kind of guess of the number? And sometimes they'll say, oh, well, it's an estimate. And I say, okay, well, yeah, then I don't actually believe a lot in the whole system, because if you're just estimating the number and making people pay based on that, then it's not really affecting your technology. You don't have some young engineer there who is given orders to really try to, try to get the airflow and the temperature right so that the emissions will be low, because they're not measuring them. So it's an estimate anyway, right? Here's the megawatt hours. That's kind of the purpose of the plant, right? So this is what they produce. Now that was another thing Carolyn talked about before, that you need a homogeneous good to compare. If you're going to base something on output, we need to be able to measure output. Now the energy, we have energy plants in here, and their purpose is to produce energy, but there are actually several kinds of energy. And that plant over there, for instance, it could produce both electricity and hot water. And we have a lot of hot water. So the hot water here comes from that plant over there, and from Volvo and the refineries and the waste incineration. It's all sort of mixed, and there are pipes under Gothenburg. The whole city is jointly heated. This is a big, expensive system. And so we need to aggregate heat and electricity. And if you asked someone who had studied some thermodynamics, you'd say you don't add them like 1 megawatt hour plus another megawatt hour, because electricity is a bit more valuable. With 1 megawatt hour of electricity, you can easily make 3 or 4 megawatt hours of heat with the help of a heat pump, right? Or turn this around, you need 3 megawatt hours of heat in a furnace to make 1 megawatt hour of electricity. So you shouldn't really add them, but we do that. We just add them, which is actually an implicit subsidy to the municipally run district heating systems. It's just one of these small details, right? Also, there are some plants in here, well, this is waste incineration. There's chemical industry up there. So they might be making plastics or whatever. They are in this system basically just judged on how much heat they make. So the fact that you afterwards make chemicals with that heat is like irrelevant here. We're just taking like furnaces, and we're measuring the output of each furnace by its thermal heat production. So you can calculate the phi. The phi is the NOx times 40. Well, this is, yeah, right. This times 40 gives you this. And then you get a whole lot of money here, which is the sum of all the fees. It was about 1 billion in the originally, 1 billion krona. And that is, so to speak, put in a hat. But I mean, of course, that's the purpose of an Excel sheet. An Excel sheet is like a hat, okay? So you just divide the total revenues by the total megawatt hours, and you get a refund, which in this case is 9 kroner per megawatt hour. Megawatt hour is 1,000 kilowatt hours. And a kilowatt hour is something you could sell. Well, if it's heat, it's cheap. If it's electricity, it's 1 krona. But say it's worth 300 krona or something. So you get a refund of 10. It's not insignificant, but it's not enormous. This is not the main product that they're producing, right? Okay, this is just a side benefit. And then you calculate the refund for each industry. It's easy. It's the 9 times. You know. And the cost of this whole system is like one guy who does this on Fridays. It's not expensive. I mean, this system is run by the Swedish EPA at virtually no cost. There is a cost at each plant to monitor. And of course the monitors have to be monitored as well. You have to, every now and then you have to send an inspector to check that the people in the plant are not cheating with their monitoring equipment and that. So there are some costs. But the actual calculation of this is really remarkably cheap. So I think that helps, you know, explain. And we'll explore the differences between this and a tax. And a tax has a number of effects, right? It changes your technology. And there could be an incentive to, you know, to put in catalytic converters or to change fuel. There's this effect on the price of the product. So the price of hot water and of electricity and other stuff will be more expensive. That's the output effect that Karen has been talking about. So then there's an incentive. If a tax, an optimal tax, would have the effect of making things a bit more expensive so that people would use them a bit less and people would perhaps turn off the heat. And then there's also a tax has an effect on the budget, right? The budget, if this had been a tax, it would have gone to Anders Borg, and his job of balancing the budget would have been a bit easier. He could have lowered some other tax. So there are effects all through society, but they're on the whole still, these are small effects because this is, compared to the Swedish budget, this is not a lot of money. And there are these tax interaction effects that Karen spoke about. So if you already, I mean, an optimal society, the company would be looking at the opportunity cost of labor. That should really be the cost in a way without the tax. And the tax is distorting some of the decisions of how much to work and how many people to employ. If you have that kind of distortion, I mean, it's a distortion, because we want a society with public goods, but it's a distortion compared to the simple model that we have of firm behavior and household behavior. And then if you put on more distortions, there are interactions between these distortions. So, there's a pointer here. So, the incentives for the firm are given by this equation in this case, and it's very similar to the ones Karen already showed. They make their profit by making output, QI, multiplied by big P, which is the price of their product. And they have costs that depend on how much they produce and how much they abate. They have to pay a tax, that is a fee in this case, on the emissions, which depend on, again, on output and abatement. And then they get this refund. Sigma I is their share. their share of output, which typically, I mean, when this system started, there were 200 firms in there. And of course, some firms could be bigger than others, but I think the biggest firm had a share of maybe 2% or something. So sigma is typically rather a small number, times the total tax revenue, all the money collected. So when you're going to take partial derivatives of this with respect to Q and A, you see there are Q's and A's in there as well. And so you get slightly different. And the incentive to abate, to choose clean technology here, is almost, the red is what you would get for a tax, a Pigouvian tax, which is the optimal instrument. And so you can see there's actually a small deviation from that here. The incentive to abate is the optimal sort of marginal cost, the tax times the marginal emission of with respect to abatement, times this 1 minus sigma. But 1 minus sigma would typically be 0.99 or even more. So it's actually, it's a tiny effect. And sometimes I feel that, you know, that we as a profession have been chasing this, and it's a fairly small thing, because we forget that T here would be really different. If this had been a tax, even in Sweden, the most tax-loving country in the world, it would never have been 40 crowns per kilo. It would have maybe been 4. It would have been impossible to get through Swedish Parliament a tax, you know, taking into account all these things that I said, that you're only taxing big companies and not small companies, you're not taxing the Danes, and all these other things. There would have been a giant resistance to a tax. Is it getting cold?
Yeah.
Oh, I'll close it. It's just, I get warm because I'm lecturing. So we must remember that when we compare instruments and say which is optimal, that the T that is politically feasible is quite different. I'll talk a bit about that, a bit more about that in a moment. Then the output effect. And there is actually a bigger effect. So the difference in the incentive for clean technology is really small. The difference in effect on the output, that is the decision that the firm will take, am I going to produce 1 megawatt hour more or not? That decision is actually changed, because this is a small effect here, but this is quite a big effect over here. And as Carolyn was sort of saying, normally if you have a tax, you would sort of, am I going to produce a bit more? Then if you produce more, you emit more, and you have to pay that tax. With a refunded emission payment, you produce more, you have to pay the tax, but you get more refund because you're producing more. So that there is a distortion there. So yeah, conclusions of this is the abatement incentives are roughly the same. The output incentive is different. The average firm pays nothing. You can see this as a competition, with the dirty firms paying to the clean firms. And that is kind of interesting. So there is a political dynamics that is quite different, and I'm interested in lobbying, right? I think that a lot of policy making is actually more affected by lobbying and by who pays than by optimality. And we as a profession, we spend a lot of time thinking about optimality. But then, like, the number of people who care about optimality, that is actually basically the economists. Everybody else should care about it according to our theory, but in reality they're obsessed by who pays, right? And if a government committee sort of suggests a tax, the whole industry association has their secret meetings and starts preparing meetings and starts taking the minister out for lunch, and you know, there is all the way from sort of academic persuasion through corruption at the other end in trying to stop the proposal of the law. When you have a refunded emission payment scheme, as we now have here, they were talking about increasing it the other year. What does the lobby? The lobby, can they have a meeting, and then half their members say, oh, well, we actually like this. We're making money out of this scheme. So then the chairman of the lobby association, the industrial association, had his hands tied behind his back. He doesn't know what to say. Yeah, next time he meets the ministry, he says, yeah, well, half my members like the scheme. You know, it completely reduces the power of the lobbying, because it divides the lobby in half. And so I think in this particular case anyway, that has been the most important thing. You would never have gotten 40, now it's been raised to 50 kroner per kilo. You would have had a few kroner per kilo, and a few kroner per kilo would have had very little effect. So it's important to basically destroy the power of the lobby. It's also happens, as Carolyn mentioned, to be an optimal instrument when you have some market power. I don't know if you've seen this. I like this diagram with what happens when you have a monopoly. You know, suppose you have the demand for a product here, and a marginal cost of production, then the optimum would be here in just simple market, you know. But if there is an externality involved, then we should really reflect that, and the optimum with the externality would be here instead. So that's the kind of the reason why we have a tax. But suppose this had been a monopoly. Well, then you know the monopoly would be producing where the marginal revenue cuts the marginal cost curve. Because the monopolist can choose whichever point he likes here. He's not bound. The logic of this intersection is that if the producers try to sell more expensively, some other producer will undercut and sell cheaper. If there's just one producer, that doesn't happen. The one producer can choose whichever point he likes. And he does that, it's easy to show, by equating marginal revenue equals marginal cost, and he would choose this point up here, and this price, which is far away from, that's why we don't like monopolies. It's far away. The monopoly produces a small amount at a high price. Now, if you put a tax on this, if you put a tax, let's say this is electricity, and you put a tax on the carbon, well, then you're increasing the marginal cost, and you move this slightly, this point, from here to here, and you get up to this point. And the interesting thing is, you're moving away from the optimum. The optimum was here. The social optimum is here, which takes the tax into account. But compared to what would have been a free market equilibrium, if you put a tax on a monopolist, he produces even less. He's already producing too little. And you make things worse. Now, with an oligopoly, similar things happen, but it's much more complicated, right?
Again, you can't let them know that you're giving them their own emissions revenues back.
Yes. Yes, right.
If the monopolist knows that he gets all his tax revenues back, there's absolutely no incentive to do anything.
Right. And so Riquate and Gershbach, they showed that in an oligopoly with identical firms, that in fact the refunded emission payment is the optimal instrument. That it is actually optimal to not have this output effect. So that's kind of related to the fact that oligopolies already underproduce.
Well, they don't say that 100% rebating is optimal. They say that you can find an optimal rebate, but it might be more than 100%, it might be less. It depends.
Right.
So
some amount of rebating is optimal. Yeah, well, I already mentioned this. I wrote an article with Per Fredriksson showing that if you have a model, in which the level of the tax is decided by lobbying, where you have lobbyists spending money and the more money they spend, the more they manage to get the tax down. Then with this kind of refunded emission payment, the lobby is so much weakened that you get closer to the optimum. Now look a bit about what has happened in this scheme. NOx abatement is not easy, by the way, we found emissions have gone down quite a lot. In fact, this is what you get in the scheme as a whole, but that's because they brought in new industries all the time. So after a few years in 95 or something, they said, okay, we won't just take the plants that produce more than 50 gigawatt hours, we'll lower this to 40, and then they lowered it to 25. And so in the blue line here, the composition of industries is changing, and you've got more smaller plants. If you just look at the original 190 plants, you have a bigger reduction. A reduction of about half, which for NOx is already quite a lot. We've looked a little bit about the distribution of the fees. It turns out that the energy sector makes a lot of money out of this scheme, and the pulper and paper industry pays quite a lot. In fact, all the other industries basically pay quite a lot. And this is in fact related to this small asymmetry, I think, of counting the gigawatt hours of heat as if they were gigawatt hours of electricity, which is a bit of a subsidy for the energy industry. And so that's maybe a detail that could have been done differently. Here I have some, this is the Swedish plants here, NOx emissions per expressed in the same units. They're very much lower than the US plants, the same point. And that is partly an unfair comparison because you've got different fuels and different things, but still the difference is very big. And there was a big US inquiry on NOx emissions that also identified this fee as being one of the main reasons why Swedish power plants have the lowest NOx emission levels that you kind of find anywhere. And well, so we're looking at what happens to technology, and these are emission coefficients, and you see that not only have they been reduced, but the spread has also been lessened amongst the different plants. So it seems that there are several processes going on here. These are histograms, so this line represents all the plants and their individual emission coefficients ordered. And the best plants are getting lower emissions, That's quite a lot. It's gone from 0.1 to 0. Nothing here almost. An improvement almost by a factor 10. That must be basically what we can call innovation. Right? The best plants are getting better over time. But then also the sort of the angle here is going down. That must be diffusion. So the bad firms are learning from the best firms. So first you have some plants here making new inventions or new ways of doing this, and then that is spreading. So we have innovation and diffusion here. And at the end you see some plants with outrageously high emission rates. And that's the same every year. These are typically reserve plants, plants that break down, plants where the measuring equipment breaks down. There can be all kinds of explanations. It's usually just a handful of plants. And so I didn't put, oh yeah, that's right, I was using this. Didn't put too much effort into analyzing those, just looked at the rate of innovation and diffusion. This is the progress of the best plants, and this is the slope on that curve. So this measures innovation, this measures diffusion, and both those processes are going on. So there's two kinds of technological improvement here. It's also kind of fun to see, well, if you take the same plant in like 1992 and then 2005, you'll find let me see, yes, you find under this line here, you'll find plants that have improved. And you'll see there are a few plants that actually got worse. For whatever reason, whether they get older or, if this is a plant that's going to close down anyway soon, maybe you don't invest in reducing emissions, you just pay the fee. You'd also sort of, well, I'm suggesting that that this had a big effect on innovation, and so another way of looking at that is by looking at patents. Sweden is a really small country, but you see here these black are patents in Sweden, and Sweden has a high and in fact increasing share of patents in NOx reduction technology. The other countries are being sort of Germany and Japan, which are always dominant in that. I mean, they have this sort of, they are the centers of combustion technology. But the fact that Sweden is getting this large share of patents in this area is due to the fact that Sweden has kind of become a hotbed of innovation to meet the fee. It was important to have monitoring and a high price signal. And to get those two things, you needed to have refunding. And the refunding does have all these properties that we talked about. I want briefly to show you another innovation that just happened in the last few years. The Norwegians have come up with something different. Right? It's kind of exciting. They have to, because of something called the Gothenburg Protocol, this is part of this big European acidification work. There was a protocol signed in Gothenburg, and Norway has to reduce their NOx emissions, and they were having difficulty meeting this target. So in 2007, they decided on a tax of 16 Norwegian kroner, which are worth a lot more than the Swedish ones, per kilo. But still, this is still quite a bit lower than the 40, 50 that we're now paying in the fee. But then a guy called Geir Høibu comes along, Where's the guy? There we are. And says, okay, government, I'll sort this problem out for you. If you let the companies that would pay the tax join my club instead, then I promise I will deliver the emission reductions you would have got. And the rules of his club are that instead of paying 16 kroner, you pay a fee to Geir Høiby of 4 kroner. And he uses that money to subsidize your abatement investments. Right? So now it's not refunding in proportion to output, it's refunding in proportion to abatement investments. Decided by Geir Høiby. And where was I? Here. So there's some, again, there are these little funny details, rather like we had this equivalence between the thermal and the electric gigawatt hours. I think there are some that are worse in this system. So he's actually charging 4 kroner for most of industry. Industry in Norway in this case is ships, actually. So I should say they don't have that many big furnaces. They have a lot of big ships and offshore oil rigs. And those are the sources. And the ones that belong to the state have to pay 12 kroner. And the ones that private pay 4. This is a really strange idiosyncrasy, but that, you know, but anyway, these things happen. And of course the state oil sector, I mean, that's the other thing, the state oil sector is very rich and pays quite a lot of Norwegian taxes on their profit, and for various reasons they don't care how much they pay to the NOx fund, because like it's there. So it's kind of easy to ask them for 12 instead of, you know, it's 12, the tax would have been 16, it's all deductible for them and they're washing money anyway, so they pay 12, and they're happy with that. And then these ship owners pay 4. And so, and the money is used, and basically this is changing motors and putting catalytic, and they're actually not measuring the NOx emissions. So normally I would think this is a useless scheme, but on the other hand, it seems that you can't put measuring equipment on the ship of a, what's it called, the chimney of a ship. It's just too complicated. But you still want a catalytic converter there, and you kind of know that a catalytic converter will reduce emissions. So it's still a good idea to put catalytic converters on these chimneys. Well, this is actually some. How
do they monitor whether what's-his-face is delivering?
Well, they calculate the number of, you know, it's rule of thumb. I mean, they calculate the number of catalytic converters that are put on ships, and they do test measurements. They don't do continuous time measurements. So they do, you know, they put the thing on and then they'll run the ship a bit and they'll sort of measure the amount of emissions. And so then they have a fairly good estimate of the emission reduction. And Geir has to, you know, deliver this. And he's doing well. I mean, the scheme is working beautifully. You got something else come in there. There we are. Most of the investments are SCR, that is selective catalytic reduction. There's also some SNCR, non-catalytic, there's rebuilding engines, there's all kinds of things. And, you know, you can imagine a new engine. I mean, so a ship owner gets a new engine. Is that really because of the NOx or not? And, you know, well, it reduces the NOx. At the end of the day, you know, you're subsidizing emissions here. So you the company is not paying the full cost of the abatement emission. They're paying 25% of it, 75% is a subsidy, and there is the fund has a budget condition that the subsidies they pay, S times A, must equal to the over time, must equal to the fees they collect. And so, yeah, that's a little detail too. It actually seems, I mean, our overall impression, and this is still work in progress that we're working on this, it looks like this has the potential, under special conditions, you know, to be quite efficient and actually deliver a lot of abatement at a low level of a feed, because you're combining a subsidy on the abatement with the tax on the emissions, and again with all the special conditions that are around, it looks like an interesting combination. There was one diagram I skipped before that I wanted to show here as well. There is another study we're working on at the moment with a former PhD student here, Jorge Bonilla from Colombia. He had a chapter in his thesis, and Cristina Molin was on that paper too, where we looked at the Swedish industries, because they're not only paying a NOx emission fee and a sulfur tax, they're also paying very high carbon taxes in Sweden, and some of them are paying Swedish carbon taxes, and some of them are paying the fee, the emission price in the European trading scheme. And so they are switching. If you pay a carbon tax and you want to avoid carbon emissions, then you want to do things like burning wood instead of oil, because the wood counts like zero carbon dioxide, because trees capture carbon when they grow. You also want a high temperature in your furnace, because a high temperature gives you more energy per unit of carbon emissions for, well, technical reasons. And but then it also gives more NOx. So there is a trade-off between your carbon policy and your nitrogen policy, and we try to trace that substitution to see whether these are substitutes. They could be complements as well. Like generally improving your furnace, you could reduce both carbon dioxide and NOx. But increasing the temperature, you reduce carbon and you increase NOx. So there's the domain of substitutability and complementarity between these two policies varies according to a number of circumstances. So and finally we got to lunch.